In April 2025, a major headline suddenly spread across the world that seemed to answer one of humanity's oldest questions. Astronomers using the James Webb Space Telescope announced they'd detected a molecule in the atmosphere of a distant exoplanet that, on Earth, is produced almost exclusively by living organisms. For a few weeks, it felt like we might be standing at the edge of the biggest discovery in the entire history of science, the kind of moment textbooks would remember for centuries to come. Then, over the following year, a wave of independent research teams went back through the same data, ran their own careful analysis, and came to a very different conclusion than the one that first made headlines. This is the real, full story of K2-18b. Not a confirmed discovery of alien life, and not a hoax either, but something more interesting than either of those extremes. A live, ongoing demonstration of how science actually polices its own biggest, most consequential claims. It's worth being direct about something before going any further. There is no telescope finding, from James Webb or anywhere else, that has established anything resembling a 99.9% chance of life on any known planet in this galaxy or beyond it. That specific figure doesn't correspond to any real published study, any statistical framework used in this field, or any statement made by any of the scientists actually involved in this research. What does exist is a genuinely fascinating, still unfolding scientific controversy, built on real data, real named researchers, and a real contested statistical claim. And that actual story turns out to be far more interesting than the invented headline, precisely because it shows you what a real, high-stakes scientific debate actually looks like while it's still being fought out. K2-18b is a sub-Neptune exoplanet, roughly 6 times the mass of Earth, orbiting a cool red dwarf star called K2-18, about 124 light-years away, in the constellation Leo. It sits within its star's habitable zone, the region where temperatures could theoretically allow liquid water to exist, and its estimated equilibrium temperature is similar to, or modestly cooler than, Earth's. That combination made it an early favorite candidate for something astronomers call a Hycean world, a proposed category of planet featuring a liquid water ocean sitting beneath a thick, hydrogen-rich atmosphere, a configuration that doesn't exist anywhere in our own solar system, but that models suggest could plausibly host life if the right ingredients came together. Sub-Neptunes like K2-18b are worth understanding on their own terms, because they represent a category of planet with no direct analog anywhere in our own solar system. Larger than Earth, but smaller than Neptune, these worlds are thought to be extremely common throughout the galaxy based on data from planet hunting missions like Kepler, yet astronomers still don't have a single confirmed close-up example within reach of a spacecraft to study directly, unlike the handful of sub-Neptune adjacent worlds that at least sit within our own solar system's outer reaches. That makes every scrap of atmospheric data JWST can extract from a sub-Neptune like K2-18b disproportionately valuable, since it's one of very few real physical windows into an entire category of planet that may turn out to be the single most common type of world in the galaxy, despite having no equivalent circling our own sun. In 2023, a research team led by Niku Madhusudan at the University of Cambridge used JWST to detect methane and carbon dioxide in K2 or 18b's atmosphere, along with a tentative, low-confidence hint of something more provocative: dimethyl sulfide, commonly abbreviated as DMS. On Earth, DMS is produced almost entirely by marine phytoplankton and algae, making it one of the most closely watched candidate biosignature gases in the search for extraterrestrial life. It's considered a particularly promising biosignature candidate precisely because its production pathway on Earth is so overwhelmingly dominated by biology, and because it breaks down relatively quickly once released into an atmosphere, meaning any detectable quantity would suggest something was actively producing it on an ongoing basis, rather than the gas simply having accumulated from some ancient, long-dormant source. That 2023 detection was intriguing but statistically weak, not nearly strong enough to make headlines on its own. That changed in April 2025, when Madhusudan's team published a new analysis using fresh JWST data collected with the telescope's mid-infrared instrument, covering a wavelength range from 5 to 12 microns. This time, the signal was stronger. The team reported spectral features consistent with DMS and a related molecule, dimethyl disulfide, or DMDS, at roughly 3 sigma statistical confidence. It's worth understanding exactly what 3 sigma does and doesn't mean, because a lot of the coverage that followed blurred this distinction. In statistics, sigma is a measure of how unlikely a result is to have occurred purely by random chance. 3 sigma confidence corresponds to roughly a 99. 7% likelihood that the detected signal isn't simply noise, a meaningful but not overwhelming level of statistical confidence. For comparison, particle physicists generally require 5 sigma confidence, corresponding to roughly a 99. 99% likelihood before they're willing to announce a genuinely new discovery, precisely because rigorous fields have learned from hard experience that 3 sigma results frequently don't hold up under further scrutiny. That's not a small technical footnote. It's the entire reason so much subsequent research effort went into testing this specific claim so aggressively. A result confident enough to be genuinely interesting, but not yet confident enough to be considered settled, is exactly the kind of finding that draws the most intense follow-up scrutiny from a field that has been burned before by exciting results that didn't survive independent replication. A pattern seen repeatedly enough across the history of exoplanet research that experienced scientists have learned to treat any single paper, borderline significance claim with automatic, built-in caution, regardless of how exciting its implications might initially appear. And critically, even a fully confirmed detection of DMS itself would only establish that the molecule was present in the atmosphere. It would not, on its own, prove that molecule was produced by biology, since researchers have also identified potential, non-biological, purely chemical pathways that could theoretically produce DMS as well. Even with those caveats built directly into the original paper, the announcement generated enormous public attention. Madhusudan himself was quoted, describing the findings as potentially the strongest evidence yet that life might exist beyond our solar system. Careful phrasing that nonetheless traveled through media coverage in a considerably more dramatic form by the time it reached general audiences, morphing along the way into declarations that scientists had essentially found alien life. That gap between a scientist's carefully hedged original statement and the considerably more confident version that eventually reaches a mass audience is a familiar pattern in science communication. And it's a large part of why so many people came away from this news cycle with an impression of certainty the underlying research never actually claimed, a gap that widens further with each successive retelling as the story moves from scientific paper to press release to news article to social media summary. Serious, sustained scientific scrutiny followed almost immediately, which is exactly how the peer review and replication process is supposed to work for a claim this significant. Over the following year, multiple independent research teams obtained the same publicly available JWST data and ran their own separate analyses using different statistical methods, different assumptions about the planet's atmospheric composition, and different techniques for filtering out instrumental noise. This kind of rapid, coordinated, independent verification is only possible because JWST data becomes publicly available to the broader research community, meaning any qualified team anywhere in the world can pull the exact same raw spectra the original researchers worked with and check the analysis for themselves, rather than simply having to trust the first team's conclusions. The results were not encouraging for the original DMS claim. A reanalysis led by Schmidt and colleagues in 2025 confirmed the presence of methane at a robust 4 sigma confidence level, but found no statistically significant evidence for either carbon dioxide or DMS in the same dataset. Researchers named Taylor and separately Lukey and colleagues both concluded there was no statistically significant evidence for DMS or DMDS at all, noting that the specific spectral features being interpreted as DMS sat right at the threshold of instrumental noise and weren't uniquely attributable to that molecule, since multiple other sulfur or carbon-based compounds could plausibly produce very similar signals in the data. Lukey's team went further, conducting what's described as a joint analysis spanning the full panchromatic spectrum across 3 separate JWST instruments, NIRIS, NIRSPEC, and MIRI, combining every available wavelength range into a single, more comprehensive dataset than any previous analysis had attempted, and still found insufficient evidence to support either DMS or DMDS specifically, concluding that various other molecules containing similar methyl functional groups could fit the observed data equally well. A team led by Wellbanks, using what's called an agnostic retrieval approach, deliberately avoiding assumptions about which specific molecules were likely to be present, and instead letting the data itself suggest candidates, reached a similar conclusion. The current data simply doesn't robustly constrain any particular biosignature gas and remains equally consistent with a range of non-biological molecules. That agnostic approach is considered methodologically important precisely because it removes a potential source of bias. If a research team starts an analysis already expecting to find DMS specifically, that expectation can subtly shape how ambiguous features in noisy data end up getting interpreted. Deliberately searching without that kind of starting assumption is one of the more rigorous ways to test whether an original finding holds up on its own merits. Separately, a team led by Niraula and Pika Chiamara conducted what might be the most exhaustive search yet, systematically testing K2-18b's atmospheric data against a model space spanning contributions from 661 different candidate molecules, specifically to identify viable alternative explanations for the spectral features originally attributed to DMS and DMDS, an effort that dwarfs the scope of any single prior analysis in terms of sheer combinatorial thoroughness. That kind of wide-ranging brute force search reflects just how seriously the broader research community has taken the responsibility of ruling out alternative explanations before any biosignature claim can be considered credible. A level of collective diligence rarely applied this intensively to any single exoplanet finding in the field's history. Perhaps the most striking rebuttal came from a team led by Kevin Stevenson at Johns Hopkins Applied Physics Laboratory, whose 2025 paper carried an unusually direct title: K2-18b does not meet the standards of evidence for life. Using independent data reduction and their own retrieval framework, Stevenson's team found that 5% of their analytical approaches did not support the original DMS or DMDS detection at all. They did confirm the presence of methane and carbon dioxide, and found that where large features did show up in the mid-infrared data, they were statistically in tension with the smaller, more reliable features seen in the same planet's near-infrared spectrum, the kind of inconsistency that points toward instrumental red noise rather than a genuine atmospheric signal. Their conclusion was blunt. There is, as of their analysis, no statistically significant evidence for biosignatures in K2-18b's atmosphere. Given how much public attention the original claim had generated, NASA itself commissioned a more structured, formal follow-up. Renyu Hu, a scientist involved in that NASA-led effort, described the approach to Astronomy magazine, combining 4 new JWST observations of K2-18b transiting its star with the original 2023 and 2025 datasets, then applying a technique called Bayesian analysis that allowed 3 separate research teams to independently develop their own interpretations, drawing on a range of possible atmospheric compositions rather than being locked into a single predetermined model. As Hu put it, testing the robustness of a finding through multiple independent analyses is exactly the kind of check that helps confirm whether a result is real. That NASA-led study, published in mid-2025, found the evidence for DMS inconclusive, not disproven outright, but nowhere near strong enough to support the confident claims that had circulated in the weeks following the original April announcement. The choice to use 3 separate teams working independently, rather than a single unified analysis, was itself a deliberate methodological safeguard. Each team was given the same underlying observational data, but allowed to make its own choices about which atmospheric models to test, which statistical priors to assume, and how to handle the inherent uncertainties in the noisy mid-infrared spectrum. When independent teams working this way converge on a similar conclusion, despite approaching the problem from different angles, that convergence carries far more weight than any single team's result could on its own. And in this case, the convergence pointed toward genuine uncertainty rather than confirmation. It's worth noting that a formal NASA-led reanalysis of a single exoplanet's atmospheric data involving multiple independent teams working in parallel is itself a fairly unusual level of institutional attention for one specific claim. That level of resourcing reflects just how seriously the space agency treated the original announcement, not dismissing it out of hand, but also not simply accepting it, instead committing real time and real researchers to systematically checking whether it would hold up. It's worth pausing to explain why a scientific claim this significant gets put through this level of sustained adversarial checking, rather than simply being accepted or dismissed after one paper. The search for life beyond Earth touches something genuinely fundamental about how humanity understands its place in the universe, which means any claimed detection carries an enormous burden of proof. Scientists studying this exact question have proposed formal frameworks for exactly this reason. Structured standards of evidence a claimed biosignature needs to clear before it can be treated as a credible sign of life, rather than simply a molecule that happens to be associated with biology here on Earth. Those frameworks generally require, among other things, a statistically robust detection confirmed by independent teams, a ruling out of plausible non-biological formation pathways, and consistency with the broader physical and chemical environment the planet is known to have, a considerably higher bar than a single tentative detection at 3 sigma confidence, however genuinely interesting that detection might be on its own. Researchers publishing in journals like the Proceedings of the National Academy of Sciences have specifically applied these formal standards of evidence frameworks directly to the K2-18b claim, walking through each criterion in turn and concluding that the original DMS detection, on its own, fails to meet the threshold required to responsibly declare it a confirmed sign of life, regardless of how tantalizing the underlying spectral hint might be. It's worth noting that this kind of formalized skepticism isn't unique to K2-18b, or even to astrobiology specifically. Physics, medicine, and virtually every other rigorous scientific field maintains similarly demanding standards for extraordinary claims, precisely because history has repeatedly shown that early, exciting results generated from noisy, borderline data have a tendency to evaporate once subjected to careful, independent replication. The 2011 announcement of a faster-than-light neutrino measurement from the OPERA experiment in Europe, later traced to a loose fiber optic cable connection, remains one of the more famous cautionary examples from physics. A reminder that even well-funded, professionally run experiments can produce misleading results that only careful adversarial follow-up scrutiny is able to catch. Part of that skepticism comes from a hard lesson the exoplanet research community has learned repeatedly. Single, borderline significant detections and noisy astronomical data frequently don't survive independent reanalysis. That's not a flaw unique to this particular study or this particular research team. It's a structural reality of trying to extract extremely subtle chemical signals from light that's traveled 124 light years, passed through a planet's atmosphere for only a few minutes during a transit, and then been captured by instruments operating at the very edge of what current technology can achieve. The margin between faint but real signal and an artifact of instrumental noise is often thin enough that it takes several independent teams, using genuinely different methods, before the community can be confident which side of that line a given result actually falls on. Astronomers sometimes refer to this general phenomenon as a biosignature false positive, a signal that initially looks consistent with a biological explanation, but that, under closer scrutiny, turns out to have a purely physical or chemical origin instead, a possibility every serious biosignature claim has to actively rule out, rather than simply assume away. There's also the question of alternative, non-biological explanations, which any serious biosignature claim has to rule out before biology becomes the most likely interpretation. Research led by Hu and separately by Reed and colleagues has identified plausible abiotic, purely chemical pathways that could produce DMS without any life being involved at all, including photochemical reactions driven by ultraviolet starlight breaking down methane, which is robustly confirmed to exist in K2-18b's atmosphere into more complex hydrocarbon and sulfur-bearing molecules. DMS itself has even been detected in comets within our own solar system and in the interstellar medium between stars, environments with no possibility of biological activity whatsoever, demonstrating that the molecule's presence alone, even if firmly confirmed, would never be sufficient proof of life on its own. That's a genuinely important point that got lost in a lot of the initial coverage, even in the most optimistic version of this story, where DMS turns out to be robustly confirmed in future observations, that finding alone still wouldn't constitute proof of life. It would simply narrow the field of possible explanations, shifting the burden of proof toward ruling out the known abiotic pathways one by one, a process that would likely take years of additional research, even under the best-case scenario. As of the most recent published research, spanning studies released through late 2025 and into 2026, the honest scientific consensus is this: methane is robustly and repeatedly confirmed in K2-18b's atmosphere across nearly every independent analysis. Carbon dioxide's detection is more contested, confirmed in some analyses and not others. And the original claimed detection of DMS and DMDS, the specific finding that generated the signs of life headlines in the first place, has been directly disputed and in several cases outright rejected by the majority of independent research teams that have since examined the same underlying data using their own separate methods. A useful way to summarize where things currently stand is to separate the findings by how much agreement exists across the independent research teams. On methane, there's near universal agreement. It's there, confirmed at high statistical confidence by essentially every reanalysis published so far. On the broader question of what kind of atmosphere and a planetary environment K2-18b actually has, including whether the original Hycean world interpretation with a liquid ocean beneath a hydrogen envelope is even physically plausible, there's active, ongoing debate, with some researchers proposing that the planet's composition is equally consistent with an oxygen-poor sub-Neptune that doesn't require any liquid water surface, let alone life, to explain the observed data. Photochemical modeling published by Tsai and colleagues, for instance, demonstrated that K2-18b's overall atmospheric composition can be explained through purely chemical, non-biological processes, without invoking either a liquid ocean or biological activity of any kind, adding yet another layer of legitimate scientific uncertainty to the original Hycean interpretation itself, independent of the separate DMS controversy. And on the specific DMS and DMDS claim, the numbers are stark. The large majority of independent statistical retrievals conducted since the original April 2025 announcement have failed to reproduce the original team's reported detection. That doesn't mean the K2-18b story is over, or that the original research team's work was conducted improperly. Madhusudan's papers were transparent about their statistical confidence levels from the start, correctly labeling the DMS finding as tentative rather than confirmed, and explicitly calling for additional observations to test the result further. Exactly the kind of appropriately cautious framing that got lost somewhere between the original paper and the more sensational headlines that followed. Continued JWST observation time has already been allocated to gather additional transit data specifically aimed at resolving this exact question, and researchers across every side of this particular debate agree that more data, collected and analyzed independently by multiple teams using varied statistical methods, is the only way to eventually settle it one way or the other. The real value of the K2-18b saga isn't as a story about whether alien life has or hasn't been found. It's a genuinely useful, real-time illustration of how science is supposed to handle its most consequential possible claims. A research team reported a statistically tentative but genuinely interesting result. That result generated enormous public attention, some of it considerably more confident than the underlying data actually supported. And then, over the following year, the wider scientific community did exactly what it's designed to do. Multiple independent groups obtained the same data, applied their own separate methods, and rigorously tested whether the original claim held up. In this specific case, the weight of that independent scrutiny landed against the original biosignature interpretation, at least for now, based on the data currently available. That process, uncomfortable in public as it can look from the outside, is precisely how science is supposed to work when the stakes are this high. A claim doesn't become established scientific fact because one team reported it, or because it generated global headlines. It becomes established, if it ever does, only after it survives sustained adversarial testing from researchers who have every incentive to find flaws in it, precisely because catching a false claim before it becomes accepted wisdom is one of the most valuable things a scientist can do for their field. There's a certain irony worth noting here, too. The researchers who published papers disputing the original DMS claim weren't rewarded for confirming an exciting result, the way a positive detection might have been. They built entire careers' worth of credibility instead on rigorously, carefully demonstrating that a headline-grabbing claim didn't hold up. And that kind of work, less glamorous and far less likely to generate viral headlines of its own, is exactly what keeps a field like astrobiology honest. It's tempting to read this entire sequence of events as a disappointment. Astronomers thought they'd found signs of alien life, and then it turned out they probably hadn't. But that framing misses what actually happened here and undersells just how remarkable the underlying science still is, even with the DMS claim now on shaky ground. Robustly detecting methane in the atmosphere of a planet 124 light-years away, using light that's traveled for over a century before reaching an instrument stationed nearly 1 million miles from Earth, remains an extraordinary technical achievement entirely on its own. K2-18b's status as a temperate sub-Neptune sitting in its star's habitable zone, potentially hosting a Hycean-type atmosphere, remains scientifically significant regardless of how the DMS debate ultimately resolves. Consider what would have been considered a groundbreaking result in exoplanet science just 2 decades ago, confidently detecting specific molecules in the atmosphere of any planet outside our own solar system, let alone one over 100 light-years away, was simply beyond what any instrument could achieve. The fact that this entire controversy is even possible, that multiple independent teams can pull detailed spectroscopic data from a planet this distant and argue, with genuine statistical rigor, over which specific trace molecules are or aren't present, represents an almost unimaginable leap in observational capability within a remarkably short span of time. The disagreement itself is a byproduct of just how much more capable our instruments have become, and the debate itself isn't over. Researchers on every side of this disagreement continue to publish, continue to request additional JWST observation time, and continue to refine both the observational techniques and the underlying physical models being used to interpret this specific planet's atmosphere. If DMS or a similar molecule does eventually turn up with much stronger statistical confidence in future observations, and if researchers can rule out the plausible abiotic explanations that currently complicate the picture, K2-18b could genuinely become one of the most significant exoplanet discoveries in the history of astronomy. That outcome hasn't been ruled out. It simply hasn't been established yet, and won't be, until the data clears a much higher bar than it has so far. So here's the accurate version of the story that got compressed into James Webb found a planet with a 9% chance of life. Astronomers detected a genuinely interesting, statistically tentative signal in the atmosphere of a real, scientifically significant exoplanet. That signal generated one of the most closely watched controversies in modern astrobiology, precisely because the stakes of getting it right, or getting it wrong, are so high. And over the following year, the honest, rigorous, occasionally contentious process of independent scientific verification did exactly what it's supposed to do, testing a headline-grabbing claim against the hardest scrutiny the field could bring to bear. No planet with a 99% chance of life has ever been found by James Webb or anyone else, because no methodology currently exists that could produce a number like that in the first place. And no serious astrobiologist would ever attach that kind of precise-sounding confidence figure to a question that's genuinely uncertain. What has genuinely been found and is still being actively debated by named scientists at Cambridge, NASA, Johns Hopkins, and research institutions across the world is something considerably more honest and, in its own way, more compelling. A real, unresolved scientific question playing out in public with the actual data freely available for anyone qualified to check it themselves. That's ultimately a more satisfying story than a false, tidy headline could ever be. Science, done properly, rarely produces the kind of instant, unambiguous certainty that makes for the cleanest possible headline or the most shareable social media post. What it produces instead is exactly what's happened with K2 or 18b over the past 2 years. A careful, contested, still ongoing effort to figure out what a distant planet's atmosphere is actually telling us, built on real data, real disagreement, and a genuine shared commitment to not calling something settled until the evidence actually earns that label. What do you think happens next? Does K2-18b eventually clear the bar for a confirmed biosignature with more data? Or does this end up as a cautionary tale about how easily a tentative statistical result can outrun the evidence behind it once it reaches the public? And let me know what you think in the comments, and subscribe if you want to be here when the next round of K2-18b observations comes in. That's the honest, complete story worth telling.